Hello. So far we have discussed about the design bending strength calculation of a flexural member, and we have seen when calculating the design bending strength we need to know the plastic section modulus of the section, and in case of built up sections we do not have the plastic section modulus in the code. So, we need to calculate the plastic section modulus, and to know the plastic section modulus of a section we need to know how to calculate that, what is the theory behind that, and that I will discuss today, and that will be discussed through one workout example. So, first I will go through one workout example and I will see how to calculate the plastic section modulus of a section. Then as time will permit, I will go through another example where we will show that suppose if load is very high on the beam or the section is very long, the member is very long, then bending moment is quite high. So, in such cases sometimes the required section modulus will not be able to take care, means will not be sufficient on the available section. That means, whatever required section modulus is required, the available section does not have that much section modulus. So, when the required section modulus is comparatively high than the available section, then we have to go for built up section. That means, we have to use certain plates on the top of the or top and bottom of the section to increase the section modulus and to take care that much load. So, how to increase the section modulus and how to decide the thickness and width of the plate to withstand the required amount of load, that will be demonstrated through that example. So, today we will go through these two examples. So, first let us discuss about the calculation of plastic section modulus. Here you see we have given an example, that is an I section ISLB 300. We need to find out the plastic section modulus about weaker and weak and strong axis, right. That means, about y y and about z z. This section say we can say z z and this section is y y, right. So, we have to find out the plastic section modulus of this ISLB 300, and so let us go through this example. Say this is an I section whose dimensions are given. Say for ISLB 300 we know that overall depth is 300. Say let us make this as d, right. So, overall depth is d, width of the flange is bf, thickness of flange is tf, thickness of web is tw. So, this. So, now this is a symmetrical I section. So, it has equal area axis about z z and y y, which will pass through the centroid of the section. So, we can say if this is the centroid of the section, then for z z axis, about z z axis, we have to find out the plastic section modulus. That means, plastic section modulus means first we have to find out the section modulus of this, this flange. So, that will be how much? That will be the area of this flange into its means its CG distance from the neutral axis. So, this distance will be this is total d. So, this distance will be d minus 2f by 2. So, that means d by 2 minus this is d by 2 minus t f by 2, right. That means d minus t f by 2, okay. That means d minus t f by 2, okay. D minus t f by 2. So, this is one. So, I have to find out section modulus of this block into 2, because in this case also it will be, then section modulus of this area. So, this will be the area into its CG. So, CG if it is here, then this distance will be d by 2 minus T f, d by 2 minus T f by 2, right. So, this is how we will find out the section modulus. So, if I now try to find out the section modulus, say Z f, sorry, Z p z. So, Z p z will be B f into T f is the area of the flange into distance between C g of the flange and C g of the section, that is d minus T f by 2, right, d minus T f by 2, that will be d by 2 minus T f by 2, right, into 2 in 2 side. So, this is the section modulus of the flange plus section modulus of the wave. So, area of the wave will be d by 2 minus T f, this is the height into thickness is T w, into the C g will be d by 2 minus T f by 2, right. So, this will be the area into distance C g distance of the wave of one side. So, in 2 side it will be multiplied by 2, right. So, after simplifying, the Z p z value finally we will get at B f into T f into d minus T f plus T w into d minus 2 T f whole square by 4, right. So, Z p z we can find out as this. Similarly, we can find out the value of Z p y. So, for Z p y again let us draw the diagram and let us try to find out the area and its C g distance. So, this is the I section, and now about y y we have to find out, right. So, about y y if we find out, we will find out first this one, okay, and this one, right. So, for this we can find out. So, the area of this will be B f by 2 into T f of this flange, B f by 2 into T f, and C g distance will be from here it will be B f by 4, right, because total is B f by 2. So, half of that is will be B f by 4, okay. And for this portion the C g will be at the middle of this, right. So, for this the CG distance we can find out, okay, right. So, that will be T w by 2 by 2, that means T w by 4. Therefore, we can find out Z p y also. So, Z p y will be the plastic section modulus of this section into 4, because 4 this is 1, 2, 3, 4. So, B f by 2 into T f, this is the area, into C g distance from the neutral axis, that is B f by 4 into 4, right, plus area of the wave will be d minus 2 T f, this is the depth, into T w by 2 into the distance T w by 4, right, and into 2 side. So, into 2. So, after simplification we can find out B f T f into B f square by 2 plus d minus 2 T f into T w square by 4. So, Z p y value we can find out. So, that means, here we have seen that for a I section how to calculate the plastic section modulus about x axis or z axis and about y axis. So, for this particular case we have this data like d is equal to 300 for ISLB 300 at 0.369 kilonewton per meter. For this section d is equal to 300 millimeter, T w is equal to 6.7 millimeter and B f is equal to 150, T f is equal to 9.4 millimeter. So, from this data we can find out the value of plastic section modulus about z axis, that is Z p z. So, Z p z will be B f into T f into d minus T f plus T w into d minus 2 T f square by 4. So, putting the value B f as 150 and T f as 9.4, d as 300, T w as 6.7 and after calculating we could find Z p z as 542.2 into 10 cube millimeter cube. Similarly, the Z p y value we can find out. Z p y value will be T f into B f square by 4 plus d minus 2 T f into T w square by 4. So, thickness of flange was 9.4 into width of flange was 150 by 4 sorry by 2, this is by 2 plus 300 minus 2 into 9.4 by 4 into 6.7, right. So, after calculation of this we can get the value of Z p y as 108.9 into 10 cube millimeter cube. So, this is how one can find out the section modulus, means plastic section modulus of a given section, and this knowledge is useful, means will be useful for calculating the design bending strength of the member. Right. Now, I will go through another example where the available section is less, means is not available section is less than the required section. So, there we need to provide certain plate on the section and we have to increase the section modulus by addition of that plate, right. So, through this example we will see how to decide the thickness and width of the plate, that means dimension of the plate, for which the required load on the beam can be withstood. Okay. Here we see the example is given like this, that is a steel beam having a clear span of 8 mm and resting on 200 millimeter wide bearings. So, bearing length is 200 mm and clear span is 8 mm. The beam spacing is 3 meter and the beam carry a dead load of 4.5 kilonewton per meter square, including the weight of the section. The imposed load on the beam is 13.25 kilonewton per meter square and the beam depth is restricted to 500 mm. That means, the available beam depth is less than 500 mm. So, we have to be restricted with this dimension and the yield strength of the steel is 250 Newton per millimeter square and it is laterally supported, right. So, these are the given things through which we have to find out a section size, right. So, with this we can write down that the total load is given as 4.5 plus 13.25 total load, which is dead load plus imposed load as 4.5 plus 13.25, that means total load is 17.75 kilonewton per meter square. And beams are spaced at 3 meter interval, at 3 meter interval it is spaced. Okay. So, the load per meter run will be 3 into that, right. So, load per unit means meter, load per meter will be, that means W will become 17.75 into 3. This is the influence area. So, that is becoming 53.25 kilonewton per meter square. So, total factor load again we can find out, total factor load, say WU factor load. So, that is 1.5 into 53.25 because it is dead load and imposed load. So, load factor will be 1.5. So, this is coming almost 80 kilonewton per meter and effective span will be, length of the span was given 8 meter plus bearing length was given, in two sides there is a bearing length of 200 mm. So, from here it is 100 and from here it is 100. So, total length will be the clear span length plus bearing length by 2 plus bearing length by 2. So, 8 plus 2 into 0.1. Okay. So, effective length is becoming 8.2 meter. So, the maximum moment will be at the mid span, that will be, as it is a simply supported beam. So, we can consider the maximum bending moment will be W L square by 8, W L square by 8. So, maximum bending moment will be 80 into L is 8.2 square by 8, that is 672.8 kilonewton meter. Similarly, the reaction such support, that is reaction such support or shear force, that will be W L by 2. So, 8.2 into 80 by 2, that is 320 kilonewton. So, maximum bending moment is 672.8 kilonewton and maximum shear force is 328 kilonewton. Now, we have to find out the required section modulus to find a approximate section size. So, to do that we can find out ZP. ZP value we know, we can find out ZP as m by Fy by gamma m0. That means, if I put the value of m and Fy, then I can find the ZP required, 2960.32 into 10 cube millimeter cube, right. So, plastic section modulus required is 2960.32 into 10 cube millimeter cube. Now, the depth restriction is given as 500 mm. The maximum depth allowed is 500 mm. Therefore, we can see the SP6 and we can find out a section. Now, when we look through the SP6, we could see that largest plastic section modulus under 500 mm depth is ISHB 450 at 0.907, right. Largest section modulus we could achieve, which is with the restriction of the depth as below 500 as ISHB 450, where the section modulus is 2030.95. Section modulus means plastic section modulus. Okay. So, plastic section modulus of ISHB 450 is becoming this, and we cannot go beyond this size, because the maximum depth is restricted to 500 mm. Therefore, what we can do? We can strengthen with additional plate to provide the required plastic modulus. That means, we have a section with a size of depth of 450 and it could go up to 500, and up to 500 we cannot achieve this required section modulus. Means, if I consider some I section of 500 depth, we are unable to achieve this. Therefore, what we are doing? We are taking a section lesser than 500 and we are adding some plate, right. So, that the total depth does not exceed 500, means less than 500. This is D. So, sorry, capital D. So, what we have done, the I sections we have considered 450 and we are considering certain plate, so that the total depth of the section, overall depth of the section does not go beyond 500, right. So, additional plastic section modulus we have to, means we need to know. So, for this what we could see, that for ISHB 450 the section modulus is 2030.95 and we need 2960.32. So, additional plastic section modulus we have to achieve through plate, additional plastic section modulus. So, additional plastic section modulus will be the required section modulus minus the available section modulus for ISHB 450. 10 cube. So, what we need is 929.37 into 10 cube millimeter cube section modulus from plate. So, this is one. So, now I can find out the plate dimension. Another thing we have to consider, that is what will be the maximum deflection, right. So, maximum allowable deflection is the effective span 8200 by 360, the maximum deflection which can be allowed, that is coming 22.78 millimeter. So, this is the allowable deflection, and we know what is the maximum deflection coming in the member. Maximum deflection on a member we can calculate. Now, from this, if we equate the maximum allowable deflection with the maximum deflection, then I can find out the value, means value of I. Okay. Now, in this case, so to find out the required I, we can equate this, right. Now, suppose for this case, if this is W and if length is L, then we know delta is equal to 5 by 384 into W L to the power 4 by E I, right. Or I can find out I is equal to 5 by 384 into W L to the power 4 by E into delta. Okay. Now, this delta will be the, means this delta can be allowed up to this 22.78. So, from this I can find out the required I of the section. So, if I put this value, that is W was calculated as 53.25 and length is 82, right, and E is 2 into 10 to the 5 into delta is the allowable displacement is 22.78. Now, remember this W is the service load, the unfactored load, because deflection check has to be done through unfactored load. So, from this I can find out I as 68807 into 10 to the power 4 millimeter therefore. So, two conditions we got which we have to fulfill. One is the section modulus, means elastic section, one is the moment of inertia of the section which is required this to restrict the deflection within the limit, and another is the plastic section modulus required to take care the moment carrying capacity. Okay. So, these two we need to check. So, now what we can do, we can assume, because we do not know the plate thickness and plate dimension. So, we can assume any one of these, say for example, assume thickness of the plate as say 14 mm. Right. This is again a completely trial and error method, means we have to find out the thickness from the assumed value of width, or we have to find out the width from the assumed value of thickness. So, if we can assume the thickness of the plate as 14 mm, then total depth of the beam will be 450 plus 14 into 2, 478 mm. So, total depth of the beam is less than 500 mm. So, with this we can try, right, and distance between the center to center distance of the plate, the D, say dP distance between center to center of the plates will become 450 plus 14, right, 464. Distance means if we have a I section like this, and if we have plate, then distance between center to center of the plate, which we are telling as dP. Okay. So, if we have this, then the required area of plate, because from the plastic section modulus, the required area of the plate we can find as section modulus, the additional section modulus which has to be achieved through the plate, 10 cube divided by 464, right, because we need to find out the section modulus of the plate as the additional section modulus which we need to achieve, right. So, we know the section modulus of the plate will be the area into CG distance from here. Okay. So, from that if we equate, we can find out the area, right. So, area will be 2003, the area of the plate is 2003 millimeter square. Now, we can provide certain area, say let us increase say 2200 millimeter square, right. Now, the width of the plate B, width of the plate will be 2200 divided by 14. So, that is becoming 158 mm. So, let us use as say 200, right. So, plate size will be finally 200 by 14. So, we can use plate size as 214, and then the plastic section modulus of the whole section we can find out, that is 2030.95 into 10 cube plus this is the section modulus of the I section, then 200 into 14, this is the area, into CG distance 464 by 2 into 2. Okay. So, the total plastic section modulus is coming as 3330 into 10 cube, which is greater than the required section modulus, which was coming 2960.32 into 10 cube, right. So, what we could see, the required section modulus we calculated earlier at 2960.32, and we are providing section modulus 3330, which is greater than this, through these two additional plate at top and bottom, right. So, now from section modulus point of view, this is okay. Now, we have to check for deflection, right. So, with this we have to check whether the deflection is okay or not. So, here we can see that maximum I z required was 68807, right. This is the requirement, and I z provided by roll section, that is ISHB 450 is 40349.9. millimeter of the 4, right. So, maximum I z we need to provide this. So, I z provided by plate has to be this one that is I z of plate will be a r square, say 2 into 200 into 14 into r square, r means 225 plus 7, right, that is 30141 into 10 to the 4, right. So, total I z of the built up section will be the I z of ISHB 450 plus I z of plate, that means that is 40349.9 plus 30141 into 10 to the 4, right, which is becoming 70490.9 into 10 to the 4, which is greater than the required I z, that is 68807 into 10 to the 4. So, we are providing the section such that its I z is 70490 and our required I z was 68807. So, the section is okay from the deflection point of view. Moment carrying capacity of the beam of ISHB 450 section is, we can find out, that is 2030.95 into 10 cube into 250 by 1.1. So, this is the moment carrying capacity of ISHB 450, means the roll section ISHB 450 has certain moment carrying capacity which can be calculated as 461.58 kilonewton meter, right. Now, see, for a beam the bending moment is varying and maximum bending moment is coming at the center, right, and to accommodate that bending moment, to take care the maximum bending moment, we need to provide a section which consists of I section and some additional plate, right, to withstand that much moment. But the moment is not constant, it is varying and becoming 0 at support. So, we do not need to provide the plate throughout the length of the section, because unnecessary we will be providing, right, because the I section which are ISHB 450, it can take 461.5 kilonewton meter itself. So, we can find out that at what distance this moment is developing. Up to that we can provide this ISHB section, after that we can provide the plate. So, to find out this distance, we can equate M is equal to, say, reaction force at support R into x minus W x square by 2. So, if I put those value, say 461.58 into 10 to the 6 is equal to R into x. So, 328 into 10 cube into x minus 80 into 10 cube into x square by 2, right. So, I am making all Newton millimeter. So, from this I can find out x as 6397 and 1803.05, right. So, I can find out that x will be 1803.05. Okay. That means, the cutoff point I can make up to say 1800 mm. Say up to this I can provide simply I section, and after that I can provide the built up section. So, in this way I can make economy of the use of the steel, right. So, in plate girder in fact this concept will be used, so that at a particular section we will provide the required amount of steel to withstand the bending moment, and we will be go on increasing or decreasing the section size according to the requirement of the bending moment. Okay. So, today let us conclude with this. Thank you.